All right, at this point in the carboxylic acid derivative chapter, we are moving on to nitriles. And nitriles kind of look a lot different than all the other carboxylic acid derivatives, right? They have just a C triple bond to N versus oxygens in the other carboxylic acid derivatives. But the important thing that makes them kind of fit into the same basket of types of characteristics is that they have technically the same oxidation state. So nitriles have the same oxidation state as all the other carboxylic acid derivatives. So how do we define oxidation state of a carbon atom? Well, this carbon atom is attached to 3 oxygens, nitrogens, or halogens. So essentially more electronegative atoms. So there are 3 CO bonds from this carbon to oxygens. So that would be an oxidation state of 3. Same thing with this carbon here. It has 3 bonds that are CN, 3 CN bonds. So that makes it the same oxidation state. And things that have the same oxidation state have similar reactivity trends. So that's kind of why they fit together with these carboxylic acid derivatives. What else about nitriles? Well, how do we synthesize them? We technically learned how to synthesize nitriles way back in chapter 7. So chapter 7 was the introduction chapter to substitution reactions, where we went super far in depth on when it's SN1, when it's SN2, all the different characteristics of those things. And to make a nitrile, we're essentially adding this piece to a carbon skeleton. So how are we going to do that? Well, this is the partial positive, right? So we're essentially going to add a nucleophile to that. This is our electrophile. So we have an SN2 reaction of an alkyl halide. That's what this is. This could either be a chlorine, bromine, iodine, with Cn minus. And Cn minus, both the C and the N have lone pairs, and the carbon has a negative charge. And we know in this case that the carbon is the one that is nucleophilic. It's negatively charged. It's a nucleophile. So Cn minus doesn't exist by itself. We need a counter ion. So really we need just M plus. So M plus could be lithium plus, sodium plus, potassium plus. We'll just do sodium over here. So essentially we would add sodium cyanide to this reaction. We would do it in a solvent, so we can say that we would do this it's an SN2 reaction, it's a bimolecular reaction. Bimolecular reactions go at the fastest rate in a polar aprotic solvent. So something like dimethyl sulfoxide, acetone, dimethylformamide, acetonitrile, all those are good options. We'll put DMSO here, which again, remember DMSO is a sulfur double bonded to an oxygen with 2 carbons. It's just the solvent, right? It's what the reaction takes place in. And that Cn minus then will just act as a nucleophile in an SN2 reaction, kicking out that halogen to make the new carbon-carbon bond of that nitrile. And then we would get sodium X in this case as the other thing that's in that reaction. So that is how we synthesize nitriles. What is the general reactivity of nitriles? More on that in a moment. Okay, so nitriles are a carboxylic acid derivative, just like all the other carboxylic acid derivatives in this chapter. We are adding nucleophiles to them. So the question is, that hopefully you guys can answer even without me, is where would a nucleophile add to this type of molecule? I have kind of 3 locations that I've put into the course packet. So I'd pause the video right now and take a minute to decide which position, A, B, or C, the nucleophile will add to, and draw something in there. Right, Lena? Drawing's good?
Yeah.
Do you like to draw?
Yeah.
Yeah. Okay. Draw something in there to explain to yourself why that nucleophile added to that position.
I don't have an answer for that. Is there something else I can help with?
And yeah, so come on. All right, you already did that. Good job. You paused it. you figured out where the nucleophile added. So nucleophiles add to partial positives. The most electronegative atom is the nitrogen. So we could say that it's likely the atom attached directly to the nitrogen that would have the biggest partial positive. We can even back that up further by showing a resonance structure here where we demonstrate that there is a lot of positive charge on that carbon that's attached to the nitrogen because we can draw a secondary resonance structure showing a full positive on that position. So the nucleophiles do add to position B, so we wouldn't have to draw that resonance structure before we'd draw that adding there. We could just show it adding like that. That would make the nucleophile added to that position. We would have N minus, and that's what we're going to see. That's how we are going to see nitriles react with different nucleophiles. So, yeah.